welcome everyone. It's my pleasure, I guess all of us, to have Antonia Frassino with us today. Well, Antonia got her PhD from University in Frankfurt, and some postdocs in Geneva first, and Barcelona then. She has a position in Alcalá, close to Madrid, and is presently enjoying a master's degree at SISSA, where she's visiting us from. So without further ado, Antonia will tell us about extended thermodynamics, quantum inequalities, and quantum cosmic censorship.
Thank you, thank you for the presentation. Thank you for having me here. That you explained it again. So I will talk about extended thermodynamics. I will explain what does that mean. Quantum inequalities and quantum cosmic censorship on the brain. I'm going to introduce all these concepts during the time. The essential feature that I'm going to use during the talk is braneworld, the braneworld scenario. What does that mean? It's a particular scenario that was studied already during the past years, where the matter fields are supposed to be localized on a brane, while the graviton can instead propagate in an higher dimensional spacetime that we call the bulk. So yeah, we can have an higher dimensional spacetime where there is gravity, and the standard model matter fields that we see are localized on a brane, so dimension lower spacetime that is in the bulk in this higher dimensional spacetime. So one of these applications is considered the world geometries. That means that the bulk that I'm talking about, this higher dimensional spacetime, can be negatively curved. For example, it can be ADS. And this is one of these famous models called the round and soon model, where we have an anti-de Sitter spacetime that is negatively curved. And in the spacetime, there is a brane where we can find the matter and gravity as well. So the branes can be of different kinds. They can have anti-de Sitter asymptotics, in the case of hash standard brane, or they can be asymptotically flat, or they can be de Sitter. This scenario is particularly interesting, not only because it provides a way to find a hierarchy between the different forces. For example, try to explain why gravity is weaker compared to the other forces that we see, but also provides a generalization of the holographic principle, or the so-called ADS. So I already talked about ADS. I mentioned the bulk that can be negatively curved. The quantum field that we can have at the boundary of this ADS spacetime might be a conformal field theory. In the specific case of the ADS we're talking about conformal field theories. And this scenario, having a braneworld scenario, allows us to consider spacetime with boundaries. And this is what in literature is usually called braneworld holography or W holography. So another interesting thing is that in this particular scenario, so in braneworld holography, we're using ADS, we can study quantum effects on black hole geometry, because as I mentioned to you, there are both quantum fields and gravity on these branes. So we can use this model to study the effect of quantum fields on gravity, basically, and the relation that we can have with black hole thermodynamics, with geometric inequalities, like for example the Penrose inequalities, and the cosmic censorship. So try to understand what happened to the singularity. And it offers also a natural framework to explore black hole thermodynamics in a particular situation, that is when the cosmological constant is allowed to vary. For example, as we can think about in cosmology, so when there is a varying cosmological constant. In particular, so this is the outline. I will, at the beginning, I will give all the details to understand this model. So the construction of these quantum black holes, where we have gravity and also the quantum fields that are in there. I will proceed then to the study of the black hole thermodynamics. So a quantity that will be important in that framework is the generalized entropy. because we don't, not only we have the record entropy, but we also have the entropy of the fields, of the quantum fields. So the sum of the two is what is so-called generalized entropy. Then I will introduce the variation of the cosmological. I will see how is this related, how this setup allows very naturally to consider the variation of a cosmological constant. And so I will talk about this extended record thermodynamics. And then I will proceed with some geometrical inequalities and their relation with the cosmic censorship. These are the main references I will use during the talk. So I will introduce the setup that was introduced in this reference. Then some of the properties were studied in these two papers, and some of the aspects are also studied in this paper that is in collaboration with George. So any question, or George, if you feel that you want to add something, we can also. And okay, let me start with the setup. So the setup is based on this reference, and in this setup I will introduce the quantum qBTZ record. So in particular, I will focus on what is the effect of back reaction from quantum matter on a rotating spacetime. So why this is interesting? Because we, for example, we want to try to understand property of rotating black holes in the presence of quantum correction. So what is the back reaction when we have a rotating black hole? And also to study, for example, the impact of this quantum effect, the back reaction, on some common assumption in classical GR. That are, for example, the connection with the weak cosmic censorship, so the fate of the naked singularities. Usually, to study this particular problem, so what is the back reaction effect when I have a rotating black hole, it is a very difficult problem. So it's technically challenging to study this in KL black hole space. And one possibility is to go to lower dimension. So what I'm going to consider here is a 2 + 1 dimensional black hole, rotating black hole. So I will start, I will have, let's say, a qBTZ where plus the back reaction of the quantum matter. And this introduces also a good simplification, because as you know, in 3 dimension, all the quantum correction, they arise only from the matter sector, because in 3 dimension we don't have propagating degrees of freedom. So it allows to really see what is the effect of the quantum fields on the zone. In that sense, usually to study this kind of problem, to study the back reaction problem, what people usually do is to study the so-called semiclassical Einstein equation, where on the right-hand side, on this side here, we have the Einstein tensor, where there is a magic that has the back reaction, so the back reaction of the geometry. And on the other side, there is a renormalized stress energy tensor of the magnetic field. This is the so-called semiclassical Einstein equation. And usually studying this problem, it's very complicated, because we need to solve a coupled system of equations where we have the spatial magic with the back reaction and the quantum correlations on the other side. So usually it's also difficult. And the typical approach is to consider that the back reaction is small, and then work perturbatively in the back reaction parameter. So we consider the back reaction is small, so we can just expand and work perturbatively. But in some situation, it happens that we can have an alternative non-perturbative approach, and this is only for very special cases. One of these cases is offered by the ADS holography duality. So in ADS CFT, what we have, usually we have a gravity in a 4-dimensional anti-de Sitter space-time, as I mentioned before, that is represented here by the cylinder. And well, the time is running up. And this is dual to a quantum theory of 3-dimensional conformal fields. So I'm already putting ADS4 there in the bulk. And on the boundary, there are conformal field, 3-dimensional conformal fields here on this blue part. And there is a duality between these two theories. So a classical gravitational theory in the bulk and a quantum theory on the bound. what in the next part of the talk, I will always very often show this figure. This is just a circle, so it's a time slice, so a constant time slice of the antidiscrete space-time, and you see that the bulk is ADS4, so antidiscrete in 4 dimensions, and this is the boundary. So the whole disk is ADS4, and the circle it's the 3-dimensional boundary of the sphere. So you will see these figures a lot because it's exactly here that I'm gonna consider the brane I was talking about in the beginning. So in the simplest incarnation of the gauge gravity correspondence, the conformal field here, as I mentioned before, is here on the boundary and is formulated in a non-dynamical space-time. So the boundary has a fixed metric. It's non-dynamical. But there is a consistent, we can also have a consistent description where the conformal field theory lives on a dynamical space-time. And this happens by using this brane, this Karsh-Randall brane in the Karsh-Randall model. So in this case, we can have conformal fields here in on this brane, and this is a dynamical space-time, so it has a magic that can be different. So the magic on the brane, on this particular brane, this Karsh-Randall brane, is asymptotically anti-de Sitter 3, and the gravity is recovered in a 3-dimensional brane world plus the quantum fields. So on this brane, we can have both gravity and the quantum fields in this setup. So this is my bulk, and this is the brane inside the bulk. You can put this brane in a particular position and have this property. So the brane world scenario, this scenario that I just described, considering ADS and the brane inside, allows the construction of these quantum black holes that I mentioned at the beginning, this quantum BTZ black holes. And well, it was studied in previous paper, and it's based on some solutions that were found by Roberto Emparan, Horowitz, and Myers in 2000. What is the construction? So I already showed you this disk with the brane, right? And now instead of starting with an empty space-time, inside this space-time, I have a black hole. This black hole that here is depicted with this black circle, it's not a standard black hole in the center of ADS, but it's a black hole that is accelerated. So in order to have this acceleration, there is a cosmic string that is pulling the black hole. And so we have an accelerated black hole in ADS. There is a metric, a specific metric that describes this situation that is called the symmetric. And then we can slice this metric with the Karsh-Randall brane. Then, in order to complete the construction, what one does is to discard the side here on this side where there is the cosmic string that was pulling the black hole, and then glue another copy of the brane, another copy of the space-time on the other side. So we have 2 copies and then we glue them together. And in the case I'm considering, since I also want to have rotation, we see that it's also possible to add the rotation given the symmetries of the problem. In this black hole solution, there's a 4-dimensional symmetry that describes the accelerated black hole has several parameters. So there are different parameters. One of these is the acceleration that I already mentioned. And this parameter A controls the tension of the cosmic string that pulls the black hole. So if I change the acceleration, I'll change the pulling. And it can be tuned in such a way that we have a perfect situation in which we can put the brane. Because the brane also needs to satisfy some condition, for example, the Israel junction condition. Then there is another parameter that is this L4 that is related to the bulk cosmological constant, to the 4-dimensional cosmological and the cosmological constant. Then we have other 2 parameters, mu and A, that respectively control the mass and the angular momentum of the black hole. Indeed, if we put these 2 parameters to 0, basically one recover the empty ADS4. And kappa is also an additional parameter that is just a discrete parameter that can be only plus, minus 1, or 0. For example, in the case I'm going to consider, if I take kappa equals to -1, and then I perform the limits, the right limit, I will recover a standard BTZ black hole. And these are the parameters in the 4-dimensional spacetime, and they have a correspondence on the three-dimensional space, on the brane. So in the corresponding geometry on the three-dimensional brane, the acceleration is related, actually proportional, to the tension of the brane. And it's also related to the back reaction parameter. So this mu allows us to see how much back reaction from the quantum fields we're going to have in the problem. In the case of the rotating quantum BTZ metric, then having this construction, performing the right slicing of the geometry, then one can write explicitly the metric of this rotating quantum BTZ geometry. So it's very similar to what we know for the BTZ geometry. So there are the different components, the mixed component here. I'm not showing the explicit form of the metric functions because they are lengthy, but they are, it's possible to get them inclusive. And as usual, well, we can analyze what are the features of this metric. This metric has still a singularity at I equals 0. So as we can see here in this plot, there is this the function h that is the inverse of GRR. And so this part blows up for small r, so there is still a singularity at r equals 0. We can also study where is the event horizon, locate the event horizon as the largest root of this function. And there are different situations as usual. There can be two horizons, there can be no horizon here, or there can be a negative singularity. Sorry, there can be the extremal situation when the two horizons coincide, and then there can be also the negative singularity. And as I mentioned before, the classical BTZ geometry is recovered when the back reaction parameter goes to 0. Besides the rotating metric, quantum record metric, there is also the charger case that was studied and worked out this year, but it's two different groups. One in Barcelona and the other in Guadeloupe. Yes.
Yeah, I should know this because I studied this space time, but it's curious. So the 3D metric descends from the 4D ADS-C metric.
Yeah.
In the rotating case.
Yeah.
Which that's something I should know. Singularity. So you know R equals 0 is regular. For dimensional curve, black hole, there's no singularity.
Yeah, there is.
So how does it disappear in going from 4 dimensions to 3 dimensions?
Well, I guess you can always find probably a range of the parameters where some of the things are valid, whether you can find the ring singularity. I mean, the 3-dimensional metric, it always has some other feature of the 4-dimensional metric. And
but
so
the coordinate transformation that you have,
maybe that is the. I think you can still see some of the parameter space, so that you have still a ring singularity there too. Yeah, good question. In this particular case that I put here on the slide, that this is the audiometric behaves. So in this particular case here, but I can tell you better like which range of the parameter. But yes, it's possible. I think it's true that you can see the similarity also in the 3-dimensional case. Well, this was just the setup, and as you see, there are a lot of parameters, so there are a lot of different situations that can be considered. But now I'm going to go simpler, just try to understand what is the relation and to try what can we study in this setup. So this part will be related to Berkeley thermodynamics and I will refer to thermodynamic properties of the solution later in the seminar. So as we know, in the classical black hole, usually it's cold, so it has 0 temperature, but as soon as we consider quantum fields, then the laws of black hole mechanics can be translated in the laws of black hole thermodynamics. And in that case, the usual association is that there is a temperature of the associated to the black hole that is related to the surface gravity. And also what happens is that the area of the horizon can be related to the entropy of the black holes, and the mass of the black hole is interpreted as the energy of the system. And by using this analogy here, basically one can write the first law of black hole thermodynamics. That is very similar, as you can see, to the standard thermodynamics. There is another relation that is valid, that is a kind of integrated relation from the first law of black hole thermodynamics. And I'm just writing here in the case of zero cosmological constant and in 4-dimensional, because this relation depends on the dimension of the system. And it's the so-called Smart-Gibbs-Duhem relation. It can be obtained mathematically. And well, now the point is that what can we understand of the thermodynamic of this object, this quantum black hole? The bulk black hole thermodynamics translates into the thermodynamics of this black hole on the brane in the following way. So the temperature, since it's given by the surface gravity, and it's all the same always on the horizon, basically it's going to be the same also on the brane. So I can associate the temperature also to the temperature of this quantum qBTZ. And the entropy instead, as I mentioned before, since we have also quantum field on the brane, the temperature is going to be a combination of the world entropy, that is a generalization of the standard Hawking entropy in the case in which the theory contains also higher derivative terms, that is what the induced theory on the brane means, plus the entropy of the fields outside. By using this part here, by using this correspondence between the two, then one can define indeed the generalized entropy on the brane with the black hole back entropy, and also as world is given that should be given by simply by the black hole entropy on the brane. Then it's related to the generalized entropy, so it's related to the entropy of the fields on the brane. We can use this result in the black hole thermodynamics, and what we get is that it's possible to indeed have a first law on the brane that is non-trivial, and it's very similar to what we know for the black hole thermodynamics. But in this case, this first law holds exactly at all order in back reaction, because I am already considering also the effect of the quantum field on the geometry. So the fact that it's valid, well, we need to have the generalized entropy, so we need to consider both the entropy of the black hole and the entropy of the fields. And this it's non-trivial because it's made by an interplay of different quantities, some in the bulk and some on the brane. So it's the fact that this holds, it was not guaranteed, and satisfied itself. While we can also check the second one. And this is simpler because it's really based on what happened in the bulk space. What we can go now to see is what happened when we consider so that the brane is moving inside this bulk. So if the brane is moving inside the bulk, this is what happens. So from the bulk perspective, it's very natural, because I mentioned that there is a tension of the brane. It's very natural to consider that that tension can vary, and that will correspond to a different position of the brane. So for example, when the tension goes to 0, the brane is just rest at the center of ADS spacetime. So this is just the standard. We recovered the standard 4-dimensional flash with record in ADS, but the brane can also move up to this point to be very, very close to the boundary, at the boundary. If we consider this kind of situation now, what happens is that the variation of this tension correspond automatically to the variation of the cosmological constant on the brane. And this is because there is a relation between the parameters in the bulk and the parameters on the brane. And if I keep the cosmological constant in the 4-dimensional bulk fixed, automatically we can react that the variation of the tension corresponds to the variation of the cosmological constant. So this framework basically allows very naturally to include a variable cosmological constant. And this variable cosmological constant has been the matter of study of several groups already in the past, what people were trying to understand, since there is such a strict relation between black hole mechanics black hole thermodynamics and the standard form of the thermodynamics, where is it some particular term that we always see in thermodynamics, that is the PVV term. So having a variable cosmological constant allows to have this term in the first law of black hole thermodynamics, and people have studied different aspects of this problem. We have just seen that holographic braneworld offer a higher dimensional origin to this variation, to this extended black hole thermodynamics, without having to add additional hypotheses. So it's automatically obtained from the four-dimensional part. So what happens usually in the case of extended thermodynamics is that, well, people start by considering an antidesical spacetime and then identify the cosmological constant with the pressure and allow this to be a dynamical quantity. When we do this, so if we consider also this term, then we can rewrite the first law adding this additional term to consider that this is valid. And the interesting thing is that the smart formula that I showed you before, when there is a cosmological constant, it has an additional term. So we are having this additional term in the first law of the black hole thermodynamics gives us a consistency between the first law and the smart formula in antidesical. Moreover, it introduces something that is so-called the thermodynamic volume, that is the conjugate thermodynamic quantity to the pressure, and it can be defined in this way. And the interesting of this thermodynamic volume is that it satisfies some mathematical inequalities that were initially studied by this group 2011, and that they call reverse isoperimetric inequality. So there is a geometric relation that can be geometric relation between the area of the black hole and this thermodynamic volume that it's always satisfied, and it allows us to give some interpretation because, as we have seen, the area of the black hole is related to the entropy of the black hole. Moreover, it allows also to study black hole phase transition and to find interesting cases. This is just one example that I studied and after that. So in the case of the braneworld scenario, what happens? In this case, we can consider the brane tension as a thermodynamic quantity in the four-dimensional bulk, exactly as we would do with the surface, with the tension for a liquid, the surface tension of a liquid. And if we imagine to add this tension in the thermodynamic, then one would add to the first law the following term, that is related where this is a kind of area that we can obtain as a conjugate to the tension of the fluid. From the brane perspective itself, given the relation between the tension and the cosmological constant on the three-dimensional brane, this first law can be rewritten in the following way. So what we get, just taking the braneworld scenario, considering a brane that is asymptotically antidesiccant and varying the tension of the brane, so the where is the brane basically, we automatically obtain a generalization of the brane first law with the inclusion of this BP term. And we don't need to do any other assumption, just naturally tune the brane, move the brane in the space time. Now, as I mentioned before, with the black hole thermodynamics, we already get some kinetics, in some way, some quantities, like for example, the volume, the thermodynamic volume that I mentioned before, and we also have the area that is related to the entropy. So what people wanted to study is what is the relation between some of these geometric quantities. So now I'm going to talk about the reverse isoperimetric inequality that I mentioned before, and also the Penrose inequality. The reverse isoperimetric inequality are related to the standard isoperimetric inequality that, well, I can introduce like them in the Euclidean spacetime. So in the Euclidean spacetime, there is this inequality here that is called isoperimetric inequality for a volume B bounded by a surface of area A, and it basically says that a sphere has the smallest surface area for given volume. This is an Euclidean space, nothing complicated. And this is the inequality. Now, what people discover is that if we consider what people discover in this particular reference is that if we consider the thermodynamic volume B and the black hole horizon area, what is valid is the reverse superimaging inequality, and it has a physical meaning, the same as before it had a geometrical meaning. So that this reverse superimaging inequality tells us that a fixed thermodynamic volume, the Schwarzschild radius black hole, has the maximum entropy. So the Schwarzschild solution at a fixed volume always has a bigger area compared to the other solutions. So in this case, we need to compare this solution, so the area at a fixed volume, with other solution that we know, and we check that the inequality is satisfied. What we studied too is we asked the question to ourselves: what happens when we consider quantum fields? Is the same inequality valid? Do we get something different? And what we could find is a generalization, quantum generalization of this reverse superimaging inequality. Of course, in this case, we need to consider there are some subjects related to the fact that we need to consider the quantum fields. So the Casimir energy of the fields needs to be taken into account in order to have the right inequality. And we check that this inequality is satisfied. So we have a quantum version of the reverse superimaging inequality. Now, this reverse superimaging inequality, as we have seen, puts an upper bound to the area or to the entropy of the black hole by comparing the solutions of the area with other solutions, right? You remember it was this interpretation here. So we need to compare with the rotating solution, the neutral, we need to compare all the solutions that we have to the Schwarzschild. And the extension of reverse superimaging inequality includes quantum reacted spacetime, and it may serve as a guidance to try to understand what is the effect of quantum back reaction on the black hole geometry. But now we can also use another guiding principle, the Penrose, that is the Penrose inequality. And the Penrose inequality, differently from the reverse superimaging inequality, also put an upper bound, but in a different way. It doesn't require us to check that is valid for different solutions, but we can evaluate, it only requires evaluating quantities that are defined instantaneously for whatever spacetime, and we don't need to do this comparison with other solutions. And well, we can also study the Penrose inequality and have a proposal for the Penrose inequality in the case in which there are quantum effects. Now, as you know, the Penrose inequality was proposed in 1973 by Penrose. And the interesting thing is that, well, it's an inequality that relates the area of a surface, of a trapezoid surface, to the mass. And in order to get this inequality, what we need to use at a certain point is the weak cosmic censorship. That will be also useful later. So just this is the important thing. And the classical Penrose inequality in the past has been extended to include the cosmological constant already. So there is an additional term in the Penrose inequality given by the cosmological constant with some subtleties regarding the definition of the mass. And also there was also the extension to higher dimension that was done in this subject. It has also been promoted to a quantum inequality in other papers, especially by this paper here, but it was only analyzed perturbatively in that case. So what we can do now with this quantum qBTZ construction is to test the quantum Penrose inequality at all orders in back reaction. And so this was the form that was proposed by this group. But what we found is that the quantum inequality at all orders seems to be of this form. So it's a bit different from the previous one. And it is satisfied, this inequality is satisfied by the quantum qBTZ black hole. And while if we try to check the previous inequality in 3 dimensions, it's different and there are some challenges. Okay. Now, it's also unsurprising that this inequality is different from the previous one, because in 3 dimension there are some differences to take into account. And moreover, well, as I mentioned, 3-dimensional spacetime is a little bit more different from the 4-dimensional one for some reason. But also there is a difference that is conceptual now that we are considering the quantum effect, is that it also the difference with 3-dimension is that in 3-dimension, in ADS3, we cannot have arbitrary small masses because there is a gap in the mass spectrum between empty ADS and the BTZ black hole. So we don't have all the possible masses for the quantum for the BTZ. And this is in the classical, analyzing the classical solution. But this mass gap, it's not there when we consider quantum effect. So for the quantum BTZ, this mass gap is not there, and the classical conical singularity usually gets addressed by this quantum back reaction, and it is possible to form a black hole for the mass ranges that before it was not possible to have. And so we see that basically the quantum effect strengthens the cosmic censorship. And indeed, this is also a result that it is in correspondence with what has been already seen in the past, and that we saw also by performing a different analysis. So the Penrose conjecture, as you know, it says us that under reasonable assumption, singularities, for example, that can be formed in gravitational collapse, must be shielded behind the event horizon. So this is the Penrose conjecture. And in the past, some people have studied the effect of quantum back reaction on 3-dimensional black holes. And these studies, perturbative studies of the quantum back reaction, seem to suggest that quantum effects are important and strengthen the cosmic censorship. So, and also suggest that indeed there might be a quantum version of the cosmic censorship. So now having this possible solution where we can test what is the effect of the quantum field on the black hole geometry, we can try to see as well if the cosmic censorship is strengthened by the quantum effect. And indeed, the way we did it was to use the world-thought experiment. So the world experiment is the following. If we consider Kerr black holes, they have angular momentum bounded by the mass. And in the case this bounded is violated, basically one can have a naked singularity. So the idea was try to violate the bound, to try to destroy the event horizon and get the naked singularity. And the question is it possible to do that? Well, as we know from Wald and the people that studied the process afterwards, no, usually it's unsuccessful. And well, if there are some claims, usually it's because it's very fine-tuned or it's very particular situation, but still considering higher order effects would probably remove the possibility. So usually it's not possible to destroy event horizon in this way. And indeed, what we want to see was to check if that was possible in the case of when we consider quantum fields. And in this case, the parameter space of the solution is a bit different from the standard Kerr parameter spacetime. So here I have the mass as a function of J, and we see there is a range of the parameters in which there are no solutions. This is coming from the 4-dimensional theory based Davis bound. And we have different, so this upper bound, as I mentioned, coming from the holographic derivation. We have different extremer lines for different values of the back reaction parameters. So having the back reaction, basically it enlarges the space of possible black hole solution, because of the standard BTZ is just a straight line, this diagonal line here. But having different values of the back reactions, you see, can enlarge the space of possible solution. And what we can what we can check now is that perform this world thought experiment, and basically assuming the test particle, so I fix a background, we can pick an extremal background here, backward, and then compute the variation when a particle falls into the black hole and see what happens if the solution at the end is on the side of the black hole, so it's still a black hole, or it's a negative spiral. So we can check at the end if the black hole lies above or below the extremality curve. This is the experiment. This is the what Walt did, and what we are trying. We are doing now to see what is the effect of the quantum field. And in the case in which it's possible to do an analytic calculation, so for an infinitesimal variation, we see that the event horizon is not destroyed, and the black hole, if I start with a black hole in an extremal situation, remains extremal basically after the particle after the perturbation. So it remains extremal. And but if we perform a numerical scan also for particles with finite mass, so not only for an infinitesimal modification of the thing, we see that indeed it's still valid. So what happened is that the solution after the perturbation is sub-extremal. So not only it does not become negative singularity, but it's even sub-extremal. So, and this indeed suggests that the back reaction, the quantum back reaction, strengthens the cosmic censorship, because at the end I can find a solution with this. So this is the numerical exploration for different values of the rotation parameter of the black hole, different values of the back reaction parameter for different kappa. There are several parameters, and we always see that it's always in this region, in this part, it's always negative. Well, with this, I conclude. I've showed you several things. In the beginning, after introducing the setup, that it's based on this Cash-Randall setup, we have seen that the braneworld holography offers natural framework to explore what is the so-called extended thermodynamics, because just considering the variation of the tension, it's directly connected to having a pressure on the brane, so a variable pressure, variable cosmological constant on the brane. And as proof of concept, we focus on a specific type of black hole, that is this quantum BTZ, that it has some characteristics that are different from the standard BTZ black hole. And we have seen that we can have a quantum version also of some inequalities that were well studied in general relativity. So it's reverse isoperimetric inequality that relates the thermodynamic volume with the area of the black hole. And we have seen that it's possible to study also the Penrose inequality and see what is the effect at all order in perturbation. And in the end, we studied we have seen that the cosmic censorship is stronger. It makes it stronger when we consider the quantum effect of the matter, and this case of study we used this quantum BTZ black hole. Thank you for thank you.
Time for questions. So, when you're talking about these experiments and overspin of the black hole, in the classical regime, you said sort of the intuition is that the particles might come in with high angular momentum, but they get scattered, right? So there was some kind of intuitive picture as to why.
Yeah, it doesn't happen.
Do you have some intuition also in the quantum setting, like in the linear and the non-linear? Like, should we be surprised that quantum effects help, or should I be not surprised and think, okay, that's what we would expect?
It could have happened on both directions, right? That the quantum effect could go in the direction of destroying, because I think if well, the fact that we still have, so the back reaction here is enlarging in some way the space-time available for black hole solution. So I think that is one of the possibilities why, I mean, considering quantum effects, it's given more room, let's say, to the black hole solutions. So it seems that adding the quantum effect, yes, it's compared to the standard classical astronomical, it's making yeah, the interplay between the two is a little bit different. Well, from the intuition point of view, I would say that if there are other fields that are surrounding the black hole, maybe also the other interaction, what happens inside that send the particle. So this black hole, it has the effect of the back reaction of this conformal things, the current rate. So if I send the particle already, yeah, probably the fact that the strength is because also they shield more the event horizon from the possibility of sending of the possibility for the particle to go itself. I will judge you out different.
Yeah, I would like to add something, but I have, so when we started this, I had no intuition into it.
So whatever happened, you would be surprised.
Yes, or please, but previous literature indicated that it should not, you should not get the violation in the quantum. But the previous literature only could do that calculation only in a small back reaction usually. This is full back reaction. Okay? So we replace that. But also, I could look at it in a different place. So in the classical BTZ black hole, the extremal line is diagonal. In the MJ active space, the extremal line is diagonal. And in the worst case scenario, you just gain as much angular momentum as mass. And so if you start extremal, you remain extremal, you remain on the line. But the extremal lines for the quantum black holes, the BTZ black holes, are not diagonal. They have this concavity.
So you felt maybe there's a chance.
So maybe there's a chance, but it's not.
You mentioned that in so Churchill idea spacing was the one you're saturating one of the inequalities that you have, like, and then you studied the quantum part of it. Probably you mentioned something, but I was wondering if the space-time in the quantum case, is it known like which space-time saturates the inequality, if you wish, or are there any attempts to find that solution at least?
Very good question, because I mean, in this slide, the next slide, I really summarized what is the knowledge that we have about the quantum thing. So there is this approach here that is done perturbatively, and it's done at different dimension. You can actually put D equal 3 in this case, where you get something like 1 plus and then something else, right? But this is like what we found is that this is not the inequality that is saturated for this solution, the inequality that is satisfied for this solution that is that considered the back reaction at all order. So this is the inequality that has been proposed at perturbatory from people that study that perturbatory. But if we try to study that for this solution, the inequality is different. So it seems to say, so this is the knowledge up to now, this quantum Penrose inequality. There are only these two possibilities, and this is only in lower dimension, it's only in 3 dimension, because the only example that we have for this solution we do, the reaction at all order is only in 3 dimension. So this is a 3-dimensional inequality, but it's satisfied by that solution. And it's a slightly, as you can see, slightly different from this one that is in higher dimension. So there are some hints towards which one can, how can we construct a kind of Penrose inequality that considers also the quantum effects. And we know that this solution satisfies that, and we also understand physically why this is possible in this case. So in 3 dimensions, as I mentioned before, usually when you construct the black hole solution in 3 dimensions, there is the mass gap. So no tapering value is allowed, but because of the quantum effect, this is already, I mean, we can go in also in that parameter, in that range of the masses, and therefore what here seems to be featured. So this one that I would get here, that would be basically depending on this mass gap. It's not there anymore in the full quantum mech reactor black hole. But this is the knowledge up to now. For this, yes. These are what people
Yeah, you mentioned that there are no
Yes.
known examples in 4D, right? So how
in 4D. But
Okay.
this is what they propose in 4D, but it's calculated vector.
Oh,
And it seems to be different from what one got in lower dimension, while this one in lower dimension would give a different inequality. But this is the status of the art.
thanks.
Can we go back to the inverse? Exothermic? Yeah. That inequality, a solution, solution means that also.
Yes, it means black hole. Well, it depends. It can also, so we studied that also in the case of rotation. It can also be for different geometry. For example, for the black beams, and it's still satisfied.
It's fine.
In fact,
The
the one that is on this upper
one
part,
that is with a solution.
the one that is in the upper part is in the back. This is the reverses of parametric inequality. Back. Yes. But this is a proposed kind of generalization of that. And in that case, we need to consider also the energy of the quantum field. So we had to define, to try to understand what is the energy in a particular volume, such a way to have a renormalized basically volume that can satisfy the one inequality, and it tends to be that this is satisfied in that case. So yeah, this part here is the button.
You only have the different filter.
In that case, yes. In this case, there is also the conformal field. So it's a kind of semiclassical theory at all order in the background. In that case, there is also the field. Yeah, indeed. That was indeed here. There is S-gen, because we need to consider also the entropy, the world entropy that is given for the black hole on the brane, plus the entropy of the quantum field. And this volume here needs to be calculated also by taking into account. So B is the thermodynamic volume that would be the corresponding, but then we also need to consider the Casimir energy in the volume given by the quantum fields, the finite space. So that is quantum in the sense that consider also the matter field.
Doesn't need a whole rotation.
In this case, but well, the fact then that here it depends, I think, the way you want to see it. So the fact that there is a 4-dimensional classical solution in the bulk that has a relation that is always classical. Then the 3-dimensional interpretation of this solution, this quantum BTZ solution, is that it also there are some correction to the standard BTZ metric. So there is an additional term to the metric. If I, for example, consider the one that is not rotating, that additional terms consider the fact that there are the fields. So it's related to the central charge and the number of fields that I have on my brain, basically. So it's really related to the properties of the quantum fields in some way. And then the fact that the solution is not perturbative and can be interpreted in that way, it's like having it at all. So the second one, this one is really quantum, I would say, for the fact that it really includes the effect of the quantum field in different parts. For sure, I mean, in the Casimir energy, there will be also the contribution of the gravitational part, but there is also the contribution of the quantum field. So it's basically, we can get that by considering when there is no black hole solution. So in that case, on the brane, there will be only the conformal fields, so only the quantum fields. And that's what we call the Cousin limit, when there is only quantum fields in that particular background that is given, that is the background on the brane. To verify that, it's more for other solution, it's more difficult because there are no other solution that that includes. But it's verified for the rotating case, the charged case, and all the possible solutions that are available. To verify this one, that can be done in higher dimension for different geometry, for different topologies.
It's not just gravity, you know, magic fields, but classical magic.
Class.
The top.
Yeah, that they don't like react.
If you enjoyed the video, like and subscribe.